Good evening or good morning, everyone. My name is Bion Eritrea. I recently graduated from Methodist University. This research that I'm about to present was my undergraduate senior seminar project. This research was sponsored by the Department of Chemistry and Physical Science, together with the Methodist University Center for Undergraduate and Creativity. The focus of my research is the concise synthesis of difluorinated cisgengerol using selective cis bond cleavage. Let's start with some background information about cisgengerol. With that, I'm gonna have to zoom in for visualization purpose. Cisgengerol is the most biologically active constituent of ginger. It is found in the fresh rhizome of ginger. And the fresh rhizome of ginger can exist in multiple colors. Some include red rhizome, yellow rhizome, or white rhizome. Cisgengerol has many health benefits, including anti-inflammatory property, anti-cancer property, as well as antioxidant and anti-obesity. Cisgengerol also has the ability to prevent the occurrence of heart disease. So here we have the structure of a cisgengerol, and then on the compound 3 is the structure of cis-2,2-difluorinated cisgengerol, and here is our target product, the product that we want to synthesize. The only difference between a cisgengerol and then 2,2-difluorinated cisgengerol is that the cisgengerol has a 2 hydrogen in this alpha carbon position, while the 2-difluorinated cisgengerol has a 2 fluorine atom in this position. So the next question is, why are we trying to synthesize 2,2-difluorinated cisgengerol if even though the cisgengerol has so many health benefits? Well, to answer this question, understanding the effect of fluorine in the cis-difluorinated cisgengerol will help us to understand why we are trying to synthesize this compound here. So with that, I'm gonna have to explain the effect of fluorine and its reactivity in 2,2-difluorinated cisgengerol. Well, the CH bond is known to be more stable than the CF bond. So the CF bond is known to be more stable than the CH bond by about 14 kcal per mole. And then the CF bond is more polarizable than the CH bond, and is more polarized in the opposite direction than the CH bond. And then finally, the CF bond is longer than the CH bond by about 0.4 Armstrong. And then this effect of the CF bond in 2,2-difluorinated cisgengerol makes it more stable. So even though cisgengerol has the capability to have such good health benefit, but it can also have many side effects. But with this compound to be being more stable than this compound, it may have lower side effect. And then also the 2,2-difluorinated cisgengerol has the capability to mimic those health benefits. On top of that, it can have less side effects compared to the cisgengerol. Looking at the data, those 2 CF bonds found in the 2,2-difluorinated cisgengerol. So with that, there were some previous synthesis routes by other chemists. The first synthesis of cisgengerol was done in 1996 by Fukuda and his colleagues. And then with that, they were able to synthesize 2,2-difluorinated cisgengerol by a 12 steps synthesis. And the starting material was the E conformation of X2-enal, which is an aldehyde. That was the starting material, and then they were able, with that, they went through a lot of steps to synthesize the S622-difluorogengerol compound, which is this S form of 2,2-difluorinated cisgengerol. But it was found that even though they were able to synthesize it by 81% yield, But this route of synthesis was not efficient enough. The steps are way too long to be able to synthesize this compound. So with that, Dr. Kim, who's my advisor, with his postdoc advisor, Dr. Colby, they were able to introduce a new synthetic methodology for synthesizing difluorinated aldol product, which is difluorinated cisgengerol, via alpha-alpha difluoroinolate through release of trifluoroacetate. So that's a new route they came up with. And then some of the students at Methodist University followed this route of synthesis. And here was the route of synthesis. They came up with acetophenone. They started with a compound analog of acetophenone by reacting with this base, generally referred to as LIHMDS, with this fluorinated compound, triethyl trifluoroacetate. They were able to fluorinate this compound right here. And then this compound is extremely interesting because it has the non-polar carbon-carbon pi bonds here, this pi bond. This pi bond react with sileflor. Sileflor is the source of electrophilic fluorine. So since this compound is electrophilic, it's going to react with this nucleophilic side through an addition reaction to be able to synthesize compound cysteine. And this compound cysteine is going to react with this aldehyde to synthesize the 2,2-difluorinated cisgengerol. This is a possible route that they came up with, but none of the students were able to synthesize yet about that time. So, and the R can be any of this group, the naphthalene, the third butyl compound, and then the isobutyl compound here. Any of these compound can be the R constituent. And this R constituent need to be this side right here to be able to refer to as 2,2-difluorinated cisgengerol. And then coming here, this is now my reaction overview. This is actually the step that I was following while conducting this research. So I started with this starting material called vanillyl acetone. This vanillyl acetone contains a lot of acidic protons. So we have this acidic proton here, and we have 2 alpha position, and each alpha position has acidic proton. So the first step is the addition of this protecting reagent that we refer to as a TBDPSCl with a DMAP, which was the base of this reaction, and imidazole, which is also a supporting base. And then I use a dichloromethane, DCM, as the reagent of this reaction. So this step is called addition of the protecting reagent, TBDPS. And the reason why this reaction involves a protecting reagent is because we have a lot of acidic position, and we don't want this position to react. So we want to protect it so that we can use this site to be able to conduct our reaction. So we were able to successfully add this protecting reagent. And then this protected vanillyl acetone is now going to react with triethyl trifluoroacetate in the presence of LIHMDS, which is the base in this reaction, with THF, tetrahydrofuran, as a dissolvent. Then we were able to synthesize this product, which is now fluorinated. And this fluorinated form is now going to react with select-fluor, which is the source of fluorine electrophile. And this fluorine electrophile is going to react with this non-polar pi system in an addition reaction to be able to form the product of the further fluorination. This process is referred to as further fluorination. And this further fluorination now is this product, the compound 21, is now going to react with this external in aldol reaction to form actually the 2,2-difluorinated cisgengerol. But this product is protected. Remember, in the beginning, we had a protecting reagent here. So we want actually to remove this and then take back our H. So therefore, we need to deprotect it. And this deprotecting reagent TBAF is used to remove this side to add back these hydrogen atoms. And this was the reaction overview. So coming to the data portion, of the research. The first step, which is the addition of protecting group to vanillin acetone. So I started with 100 milligram of the starting material, and then I used one equivalent. And then imidazole, 3 equivalent of imidazole was used, 1 equivalent of a DMAP was used, and 3 equivalent of the protecting reagent was used. And the protecting reagent and the DMAP were actually in excess in this reaction. And we're going to see in the analysis portion if this reaction was successful or not. In the second step, we see that this reaction, this product, this is actually the product, but this step is this is starting material is actually the product of the first step, and then this reacts with this base LIHMDS in the presence of this fluorinated compound, and this is what we refer to fluorination. This actually, the actual name of this compound is actually 2,2-trifluoroethyl 2,2-trifluoroacetate. Now, I started again with 100 milligram of the compound 19, which is this protected vanillin acetone. And then I use one equivalent. I use as well 2 equivalent of compound 20, the compound 24, which is a desulfurinated compounds. And I use 2 equivalent. I also use 2 equivalent of the base. And then THF, 3 milliliter of THF was used. And then again, in the analysis portion, the result will be announced. And coming back to the result of my third step, actually, I started with the product of the second step, which is here. And then I was able to further to use Sileflor again to be able to synthesize this compound. And this is actually the structure of Sileflor. It was complex. That's why I simply refer to as Sileflor. So this one is a little bit different because I started with a 300 milligram because I was able to synthesize a lot of this product. So it gave me opportunity to scale up a little bit to be able to start with 300 milligram. And I used one equivalent of the starting material, and the Sileflor was in excess in this reaction with 2.5 equivalents. And then here the acetonitrile was used, which is a 6 milliliter in this reaction. And then here now is the analysis of the result and discussion portion of this research. So here is the NMR spectrum of this product, the first step products. That's its NMR spectrum. And then before I actually conducted this NMR spectrum, I used ChemDraw to predict the NMR for this product to see if it's going to match with this spectrum here. And then it indeed work, and they match very well. This reaction was actually successful, even though I had some starting material here, the peak of some starting material. So I have my protons, most of the protons, the aromatic protons here are mostly found between a negative, not between actually 8 and then 7. So those are found here, and here I have my singlets found here, and I have my triplet peaks found here. And then this peak can actually is from some of the starting material, or probably I needed to purify more or maybe you use the rotatory evaporation to remove some solvent. That might be solvent peak as well. So coming back now to this mass spectrum, not to the actual NMR spectrum of my second product. This spectrum is the NMR spectrum of this for this product right here. This product, that's the NMR spectrum. So, which is a compound number 20. So, this spectrum is actually a little bit different from this spectrum because we added more compound here. So again, we have our hydrogen peaks from this aromatic system here, and we have our singlet peaks here as well. And then again, we have our triplets peaks here and here. Again, we have some starting material in this spectrum. If there was probably some leftover starting material here, some peak on some of the solvent peak, the rotatory evaporator will have I needed more time to probably dry my compound before actually I run the NMR. And then what is the here? This compound is very interesting compared to this because it has a fluorine atoms. So we further analyze by conducting a fluorine NMR. And then this fluorine NMR is an indication that this reaction was really successful because we actually found our fluorine peaks between a negative 60 and negative 70. So here is our fluorine peak, and this is the expected peak. We actually expected this peak to be between this range. And we're actually very happy about this peak. So that's again a confirmation of this reaction was successful. And coming back to the spectrum of the product of my third steps. This is the spectrum of the product of my third step. This one is a little bit special because this NMR spectrum is messy. It was not the product that the spectrum that we were really expecting. It was, this region was really like messy, so we couldn't really determine what peaks were going to be these peaks. Again, we have our protons, the aromatic protons peak here for sure, and we have some of probably triplets peaks found here, but this region we are not able to analyze well. So we are not actually happy about this result. Well, thankfully, this product contains fluorine atoms. So, and then here, those fluorine atoms are different. This fluorine atom is different than this fluorine. They are not the same fluorine. So therefore, we expect two different peaks. And the fluorine NMR was going to be to give us if this reaction was actually successful. So we are really counting on the fluorine NMR. And then it ended up that this reaction was actually successful. These fluorine atom, they are triplets. Those are triplets, and we are able to form a triplet peak here, 1, 2, 3 peaks. And then this indication, this is the expansion of this peak. This is the expansion of this peak. And then again, here, these fluorine atoms are quartets, and we're able to form 4 peaks, so that gives us a quartet, and that's a beautiful, this is a beautiful graph. So this really convinced me that this reaction was successful. Thankfully, we added the fluorine NMR. And then in this research, I said earlier that I needed to use 5-step synthesis. But actually, I was only able to finish up with 3 different step synthesis because of the time constraint. By the time of my graduation, I was not able to go at the end of my research. So I conducted up to 3 steps. So in conclusion, I will say this research attempted to synthesize 2,2-difluorinated cis-ganglion by 5-step synthesis. And then only 3 steps were conducted, as I said earlier. The hydrogen NMR and the fluorine NMR for all 3 peaks were performed. And in the step one, we had a successful reaction with the presence of some starting materials. And in the second step, successful reaction also occurred, and there were present of fluorine peak that were really like satisfied. And then as for the result, but the product was not well purified, I will say. And for the step 3, we had a complete reaction because of the fluorine peaks, the 2 different fluorine peaks, the quartet and the triplet found on the NMR, fluorine NMR spectrum. So I will say overall, this new synthesis, this new route of synthesis was very efficient. It's just that I didn't have time to go at the end of my research. If not, I was confident that I was going to synthesize 2,2-difluorinated cis-ganglion. I was almost there. So for future works, I will say that I need to simply continue my research and start with the 4 steps, because I stopped from the 3rd step, use the product of the 3rd step, and then continue with the 4th step by reacting with hexanal in adult reaction to give me this protected form of 2,2-difluorinated cis-ganglion, and then remove this protecting group through the addition of TBAF, this deprotecting reagent, to be able to synthesize finally the 2,2-difluorinated cisgengerol. And as an acknowledgement, I will say, I would like to thank the Department of Chemistry and Physical Science, the Methodist University Center for Undergraduate Research and Creativity for funding our research. And also I would like to thank Ms. Larissa, our chemistry lab coordinator, for providing all the materials needed to conduct the chemical reaction of the research. And then here my references, and I would like to thank you for your attention and for giving me the opportunity to present to this platform. Thank you.